thank you very much. Thanks very much for inviting me. So yes, I am indeed Polish. So some people laugh that we all are good at skiing because we all end up with ski. That's the case. But the one thing I need to say, I'm actually a theoretician. So I worked, not only I'm Polish, but I also used to be a PhD student of German. So I worked mostly on quantum information theory, and I'm actually a member of a group of Antonio Assin at ICFO in Barcelona. So I really come from, my background is in quantum metrology, all this quantum fission information business that Rafa and Langyang and people were talking about. So this is really my background. But in ICFO there are actually two groups, and I work also with Maciek Levenstein, which is the quantum optics group, optics theory. We are theoreticians. So today I have a bit of a challenge, because I normally in conferences I speak about theoretical results, but today I would actually like to tell you about theoretical work I did for an experimental group in our institute, which is the group of Morgan Mitchell. So Morgan has a laboratory on atomic sensors, as you might guess. So he has cold atoms. Actually, what I'll be talking about will be hot vapors of atoms. And if you don't know Morgan, Morgan is the guy who did recently the Big Bell test. So if any of your PhD students were generating random numbers at work, that was probably for this Big Bell test that was recently done to violate Bell inequalities with people using internet. So this is Morgan. And actually, okay, so I titled the talk Bayesian filtering in quantum and sensors, because this is really a topic that we would like to pursue, and what today I would like to present is really a thing that recently got published, but you should really treat it as a first step in this type of business. So first of all, as you may notice, I'm going to talk about Kalman filtering, which is a special case of Bayesian filtering. So you might already, if you're familiar with the things, we're going to have linear Gaussian systems. But the idea is to use the Bayesian filtering techniques and stochastic calculus and then apply it such that we can enhance the precision of atomic sensors. And surprisingly, this has not been done before. It has been overlooked. And really this experiment, which I would hope to explain to you, please do not ask very detailed experimental questions. I might not know. I was doing the theory. I would like to present. Okay, but as I realized yesterday and the day before that we are kind of coming from different backgrounds, as a theoretician I wanted to give you a quick, some kind of flavor of what atomic sensors are about and just key aspects that we need for these things to work. So if you don't remember, maybe you did it in the undergraduate, the key about atomic sensors is the effect of pumping. So this we are talking about really 70s. This was the paper by Hopper, Review of Modern Physics. But okay, I wrote down there's this book that is now a textbook. So what is the idea? So especially looks a bit old school, but especially I chose these ones because just to emphasize it's not something really new. The idea is that we have atoms. This will be rubidium or cesium in our case, that are free. That's why we call them hot vapors. And now you shine laser on them, which is normally called the pump, in order to excite them in particular energy level structure. Okay? And now what is the key ingredient that really makes it work is the fact that there's some optical depth. So there's a certain, say, cylinder of atoms that get excited, but they get excited collectively. So from the theoretical point of view, and this is maybe what should ring a bell, now, when we talk about single spin of an atom that will have nuclear and electronic parts, for instance, I wrote it because I have some equations later, but you really are able to talk about collective atomic spin. So now you really, thanks to pumping, I just want to give this message. If you think of these pictures that people draw, which is like this generalization of a Bloch ball to J represents the angular momentum of the whole ensemble, you really are able to do it because atoms are behaving in a collective way. So there's also a debate here, still now, is it already quantumness? I would say yes, because somehow the model of pumping is semi-classical, but yes, you are exploring the fact that they have quantized energy levels. But the thing I would like you to have in mind that they behave as a coherent object. And now when I say coherent object, I use the definition of coherence from 60s, 70s. It's not what quantum information theory, for example, do now, connecting it with entanglement. And so. Okay, so just give you some review. I mean, atomic sensors, I think they found this one in 2011. I think this is there are some even better results, I mean, atomic sensors now. So what I really am talking about is a Weber-Serre magnetometer. We're trying to estimate fields. And you may notice that this is actually the time scale at which this thing preserves coherence. So we are talking about milliseconds. Okay, in terms of atomic clocks, we even go to seconds. There's a subtlety because this is a fountain clock, so it's slightly different. But why you can do this and why you can have such good, for example, sensitivity in all these applications, really the fact that, remember, we have 10 to 12 atoms. Now I have excited them all together. So really the key is that this angular momentum vector has a really long magnitude, hence I have this sensitivity. So there's one more subtlety that I want to, or fact that I want to tell you, that actually in atomic clocks, the other thing you can do, you can apply a strong magnetic field. So when you do magnetometry, you want to sense magnetic fields. So it's actually, you don't want to apply any external fields. Actually, in other applications, for example, atomic clocks, okay, it's not least atomic interferometry, so Ramsey interferometry. You also have the trick that you apply a strong magnetic field, the whole thing starts to precess. And thanks to precession, why we do this? Because you'll be able to do some kind of counterbalance, some kind of decoherence effects that turn into play, right? So remember, there's this Larmor precession. When I say Larmor precession, I mean someone applied the field and it's been rotating. Okay, and then the other concept, which is crucial, is the Faraday based measurement, so Q and D measurement. So I took this picture particularly from the paper by Deutsch and Jessen, which is, I think, if you want to learn about the physics of Faraday measurement, which I'm going to describe in a second, it's a very nice one, but there's also, it's not a new thing. I mean, there's a review by Clemens Hammerer, for instance, and it explained all the details. But what is the physics? So physics is very simple. Now I use another beam, which is the probe beam, and now the probe beam goes through the sample, and based on the angular momentum of the sample, so these were these J operators I had on the previous slide, the polarization vector, so you'd say the Jones vector of this light will be rotated. Maybe I have it, yes. So the polarization of this light will be rotated proportionally to the angular momentum of the spin ensemble in the direction of propagation. So the way I drawn it is in Z. Okay, and there's already a thing I should mention here, given that people were talking about continuous measurement, weak measurements. So there's, first of all, this is a weak measurement, weak in a sense that if you do this interaction properly, there will be higher order terms that you should take into account. Think, for example, that this is really a dipole-dipole interaction. So, for example, you could think of quadruple moments, which will be quadratic, that come in the higher order terms. So I'd say weak in that sense. On the other hand, there's another parameter that I haven't plotted here. You can also ask a question, what is the spectral frequency spectrum of the light you are shining? So if it's far detuned for the energy levels that I had on the previous slide, that means that I actually can I'm actually not doing back action. And this is important. When we want to do continuous measurement frameworks, you want to, for example, apply stochastic calculus, you'll need to be on resonance, or at least close to be on resonance with the atoms, that, for example, you would be able to claim that measuring some angle, you projected these atoms into particular state of the spin. In general, if it's weak in the sense I've drawn here, you can just say, and what I would say conditionally, that you learned what was its J value, but you were really not doing back action. You were not really interfering with them. So it's more about gaining knowledge rather than actually changing the state of the system by measuring. Okay, and this is the standard plot. So remember, we have this angular momentum that is distributed, and if they are pumped or they are polarized, what we would call it a coherent spin state. So they'll have some kind of variance in all these directions that is equal. And now, thanks to this measurement, you learn a bit of the component in Z. So what you effectively do, which is called conditional squeeze state, you kind of shrink the variance in that direction. So for instance, this is why you can then use this state of the atoms to do, for example, better sensing of magnetic field around X, because now if it starts to rotate in this direction, you will have better resolution. The one thing I want to say now is it's called condition squeeze, and how it's normally done in the lab. You normally have first second of pulses to do the light probing, to prepare the spin squeeze state, and then you do your sensing. So in the standard things that have been done in the last 10 years, there's never been continuous, it's never been done in a continuous manner. Normally you prepare it in the squeeze state and then you use it for particular task. Okay. So here I'll advertise actually results from Morgan's group, which I think is kind of nice. It's very recent, but it shows how you can push these ideas to a certain limit. So you can actually do, it's still this conditional squeezing. This is exactly their setup. You're doing this Faraday measurement. The only thing, these are cold atoms, but that's why they can make them elongated. But they are trying to do two things here, which are kind of nice. Notice that they have exactly these atoms, but they are measuring the component of one of it's the Z component of the angular momentum. But then it decays, so they can somehow also estimate its length as the component, so they do the squeezing. So notice that the big sphere is squeezed by the same mechanism I showed on the previous slide, but also it's squeezed in the direction outside of the plane. Because they are learning, with this kind of envelope, they are learning the amount of atoms they had in the trap. So this is why they would call it, it was a simultaneous tracking of both the kind of angular and the vector component. But there's another thing that people get quite excited about nowadays, because actually this allows you to, okay, I call it evade. There's people who use different names. Okay, I'll say evade Heisenberg uncertainty relation, because what you can do, as you remember, these guys follow the Heisenberg uncertainty relation, so there's the commutator here. But by preparing atoms in a state that has fx component 0, the right-hand side is 0. So that's why they are able to squeeze fy and fz at the same time.
F is the same as j?
F is the same as j. I'm sorry, this is experiment. So j is, yes, f is exactly the same as j. Sorry, I apologize, yes. So yes, but this will be only on this slide. I took it from here. So yes, very nice. Indeed, they claim that this is it's okay, they use the word tracking, so they try to claim it's a continuous measurement, but also basing on previous talks we've seen, it's not really continuous in a sense that it's a single shot. What they do really to do some kind of, to plot this X shape, they repeat the experiment 500 times and they go every time to the same spot, and then they kind of try to infer about the variances basing on many repetitions. They cannot do it based, for example, of the measurement data from the one shot that was in a single cycle. So now it's the question, can one do it? So I will not lie that this is not our invention, and really the papers that really already proposed this were papers by Hideo Mabuchi. I chose this one particular with Jeremiah. So this is exactly this idea that now I'm going to talk about single shots, so it's a single time trace. So this is the measurement I'm going to get in my Faraday so photocurrent, so this will be this angular spin. It's very noisy, I have stochastic noise. But now, thanks to the continuous measurement framework, I will be able to, as Andrew Jordan was showing for qubits, I would like to do the same now for the spin ensemble, to be able to claim with time that actually a state conditioned of this trajectory, it becomes squeezed in Z. Okay? So just to remind you and maybe connect with the things that you probably know, and then you should really apply this continuous measurement framework. So for instance, if you attended the school, like some of me as well in Marseille, you should know that if you do a homodyne measurement, this leads to a Wiener type of noise. So this Faraday measurement is also an example of homodyne measurement. So you have a Wiener type of term that describes the outcomes. This is this y that is here. And now in the standard, I took it from this work by Jeremiah Stockton, Doherty, and Mabuchi. Then you can actually describe the conditioned state of your ensemble that it's strongly back, so the back action is here strong, because now basing on the fluctuation of your measurement, you're going to say that this is the trajectory that my state is followed. And this is the standard framework of continuous measurement of homodyne detection. But there's a subtlety here, and this is why this kind of approach failed. Because if you, for example, come from spin conducting qubits, which I know here in France is very well developed, this system is very dirty. So spin conducting qubits, as I understand, they are very clean. So somehow these equations are really trusted. So for example, in this particular paper, what didn't work, they really had some phenomenological way to describe all the decoherence that is there in the system. And this is really not what's happening. So I just let you just do a bit of sidetrack and tell you what's the current status, how to describe decoherence in these systems. So when I was trying to learn this, actually, I realized that everyone really cites this paper by Appelt in 1998. It really describes all the decoherence mechanism that happen to atoms in such atomic ensemble. But giving the talk in France, in Paris, I really should say that if you go to these papers by Appelt, Hopper, and so on, really everything was done by Grostet. I don't know if I pronounce it right in French. And actually, it's a shame because all these papers are written in French. So I don't know French, so I struggled a bit. But what is the big problem? In all these descriptions, what these people typically do, they say that even though I have this big atomic ensemble of 10 to 12 atoms, I'm going to describe it as an effective model of a single atom. So I'm going to say that, okay, it's kind of big. But let's gonna say that on average, I can take this reduced density matrix, if it's permutation invariant, and describe the whole ensemble, so this huge amount by just a single density matrix of a single atom. And now it's very strange because now you have this, I wrote it for you, a complicated equation that describes different processes. Okay, they may be a bit scary, but they're not. Notice these are commutators, so these are Hamiltonians. This is interaction with the magnetic field, so this is the Larmor precessions. This is the hyperfine interaction of the nucleus with the electronic spin, so this is what's responsible by the splittings. Then you have the spin exchange interactions, and this is very weird. We are talking here about, and this is really a contribution Grostet, we are talking about atoms colliding, and when they collide, that exchange spin, but they preserve the total angular momentum. So notice that this is a two-body interaction, but we are using a formalism that really bases on a single density matrix of a single atom, and it's not surprising, and it's highly nonlinear here. So notice that this is a mean value of a spin for a given atom, so this term is nonlinear. So, okay, and then you have some kind of spin destruction collision that they collide and they lose the spin. So they collide, they had some spins, and they go away. This is due to pumping, this is due to diffusion in space, but these are normally negligible. But I want to draw your attention, and this is why this kind of approaches failed, because here, notice that already they used global operators, so they were trying to describe decoherence in a coherent manner at the level of spin ensemble, where here in the real, what people really do in this business, they use these models of a single atom and then some kind of account for effects like entanglement of interactions by some kind of nonlinearities. So this is, I think, what really comes to contrast, and this is when we came into play, which we would like to now explore. So what to do then? So the solutions go step by step. So I would like to say that the experiment and the results I would like to present is kind of step number one. So step number one for me, let's say we're going to describe the atomic, we would like to go and do this continuous measurement formalism, which has stochastic calculus in it. So let's say for a moment we're going to describe the atomic spin noise stochastically. Let's say we'll do it phenomenologically. We're just going to do very good experiments, but we would like to have such a model. So it's the first thing. Second of all, for the moment, we don't want to do the back action, because we want to verify that things work. So we're going to say, and this is this thing I mentioned, we're going to be off-resonant with our light from the atoms. so that we're going to have an independent stochastic model that models photonic shot noise. So I have atoms doing one kind of stochastic dynamics, photons doing the other, and they are somehow coupled, but the noises don't get mixed out. Okay? And then, just to verify that everything works, let's apply it to some particular task. So we're going to sense stochastic signals, which formally in the future should be the magnetic fields, for instance, that you would like to reconstruct in real time. Okay? And this is what's called waveform estimation. So the waveform estimation is the estimation of signals that vary in time, and this is it. But as a first step, we would like to do something even more simpler. So we would like to have a linear Gaussian dynamics, because in that case, we have an optimal tool that is the Kalman filter, which is the special case of Bayesian filter that works in the case when the state and measurement dynamics are linear and Gaussian. Okay? So from now on, I would like to talk directly about the experiment, about how we did it. But so I'll give you some kind of motivation, what is Kalman filter from an engineering perspective. So maybe this is how I learned it before I knew about continuous quantum measurements. So
this avoided back action means that you will not consider the squeezing of atoms.
Exactly. So this is very important. So we would like to, so that's why I call it step one. We would like to just have a model that is correct in the sense that correctly describes atoms stochastically, correctly describes photons stochastically, but we're not going to do, no. So exactly, this would, well, I hope on the previous slide I convinced you that it requires a bit of theory to be done, which I haven't done yet. Okay, so what is a Kalman filter? So Kalman filters are everywhere. So they are in touchpads. I mean, Apollo mission was the big thing because Kalman filter really made people to land on the moon. Because actually it's surprising that Kalman, I think he passed away last year and no one noticed it, but most of the devices you use, like tracking devices, they use filtering as Kalman filter. So here particularly, I chose this example. Imagine you'd like to sense where your finger is on the touchpad. So your actual position is this x variable, which is the two parameters. Okay, and now what goes into your computer is some kind of output, which is the position it tells you. And now what you'd like to do, based on the output, you'd like to say, okay, the position will actually there, and you'd like to move the cursor on the screen. No? But just to draw your attention, there's some particular dynamics that your finger does. So, for example, in this business, we're going to say the dynamics is stochastic. I wouldn't say that actually when I use computer, I do stochastic movement of my finger. There's a model that somehow that describes how the position of the finger is transferred on what is this position telling you. And then there's the estimation scheme, and notice that estimation scheme, this is the important thing. In your computer, you can have track what was the estimates previously in time. So just to give you intuition, if your sensor is telling you that you are here on the right-hand corner of the touchpad, but you know in the past you were in the left-hand corner, your estimator should take that into account, no? Because, so this is the point of filter, okay? So then, exactly, the thing you'd like to do is minimize the mean squared error. So I can now write the covariance, it's formally called the covariance matrix between your estimates and the actual positions. And you would like to minimize it, and the minimum will give you the optimal estimator how to make your touchpad work. Okay, and this, I will use the name states for position. Observation will be the sensor output, and estimator is your estimate. And now, actually, in general, if you know the Bayesian frameworks, in any problem, the optimal estimator in this framework is the mean of the posterior distribution. So if I get what's the probability of being at time t plus delta t given all the outcomes in the past? The optimal estimate is the mean of this posteriori distribution. Okay? But now in this special case on this linear Gaussian dynamics, and let me write this, so I'm writing it in the Ito calculus way, that you know that actually the state evolves stochastically and it's linear, plus it has some Wiener noise. Moreover, your observations are related in a linear way to your states, and they have some different Wiener noise, which is also Gaussian, so I call it linear Gaussian. Then we know how to solve the problem. But just to give you, to emphasize it, in waveform estimation, this is what Madeleine always emphasized to me, you know all these things. You know F, you know G, you know H. So in these problems, people tend to confuse it in tracking. I actually will know the dynamics of my finger before I start doing this. So this is a subtlety. The only thing, think of it that I know how my finger moves, but I don't know its stochastic jumps. So this is a way to actually follow the particle trajectory, but I know the dynamics. So when you go to tracking, you actually don't know the dynamics. You want to track a ship on the sea and so on with a radar or something like this. Okay, so this is the linear Gaussian model. This is Rudolf Kalman. And he really tells you how to construct this optimal estimator. And this is what's typically called the Kalman-Bussy equation. It's a differential equation that if you solve, it tells you that the optimal estimator fulfills it, and the thing that comes up here is the Kalman gain. And to get the Kalman gain, you should solve another differential equation, which is called the variance equation, which tells you the evolution of the covariance matrix in time. Notice it's quadratic, but you can solve it, I mean, it's nonlinear in that sense, but you can solve it efficiently. And moreover, you can solve it first, store it on the computer. So how to do it, and how does normal devices work? They solve this equation, they store it in the computer, and then in each time step, they construct the estimator with this Kalman gate that uses it taken from memory. So one very important point is that why is it so good, why everyone uses Kalman filters? Because they are fast and causal. So notice, okay, I wrote this as a differential equation, but it's first order differential equation. So the estimate and moment t plus delta t depends only on the previous step. So I don't actually need to store all my previous estimates. I need to construct the optimal estimator, all I need to store, that's why they are so fast. I need to remember just the last step, okay? And then it also provides you the error for free. Because if the linear model is Gaussian, then by propagating this matrix in time, it's actually you have the error bars for free. If the model was correct, you assume. But if the model was correct, you assume, it gives you the error bars for free. And moreover, this error bars, if you see it's stabilizing, it's error stabilizing, that means that actually it verifies that everything is working correctly. Okay. So now let me go to the experiment. So we will give you a spoiler. What is the motivation? So this is some kind of a spoiler what we did. We're going to apply some waveform which is stochastic to our atomic sensor. What sensor does, it has this coherence time of the atoms which completely washes out all the features of the waveform we applied. But thanks to this magic, somehow we are able to recover it in real time on the output. Okay, and what is the setup? So it's exactly like I said on first couple of slides. So we have these are rubidium atoms. We pump them. We have a strong magnetic field because we are not sensing, you'll see it, we're not sensing the magnetic field yet. And we are doing the Faraday rotation, measuring the angle that will be proportional to the angular momentum of the spins in the z direction. And again, answering Raphael's question, again, there's no measurement back action. So this is crucial. The light we shine is far detuned from the atoms, so we can treat the noises independent. Okay, so these are some experimental details I've put, but I will not lie, I haven't been in the lab while this project was going. So this is how typically these vapours look like. They're the size of a euro coin. And okay, in this case, notice that atoms, what you do, you put a sample, you heat it up to a certain temperature, and then given on the temperature, you're going to estimate how much atoms are in this, roughly in this cell. But they will very quickly collide. So there are a couple of tricks you can do. In particular, we use the buffer gas. So our technique is people use paraffin coating of cells, because if you didn't do it, decoherence would be too strong. Okay, and obviously any magnetic fields from outside will strongly destroy your sensor. So in this case, you have the shielding, which you can see. This is how it looks in the lab. And okay, in the important part that the experiments really worked hard on, they have 3 kind of dimensional coils, so they can really control the magnetic field that's happening in the sensor. Okay, and why we did this and why we could have done it, it's really a previous results that were done in the group by Gian Vito. It's really because these guys have done very good noise spectroscopy of this sensor. So what they do this measurement, they do the power spectral density. So this is a power spectral density of the measurement of the photocurrent you do. And then you can do in frequency exactly observe the peaks. And after you should go to this paper, but you have a really nice model, which is a Lorentzian model to explain what's going on. And this is really the key. Once we had this, we had the properties of the noise, of the stochastic noise of the atoms. And let me tell you why. Okay, I'm simplifying a bit, but in this Lorentzian picture, so you can think the shift. Okay, I've put 0 here, but 0 actually I offset by this SF. So there's this offset here plus the Lorentzian on top. The offset is actually due to photons. So it tells you about the photons. So it's the photon shot noise. This is the relaxation. This is how quickly you lose the coherence, how quickly your vector shrinks. And this is the noise of the atoms. So for example, actually what this means that you can describe the atomic by spin dynamics by Ornstein-Uhlenbeck process. And this is exactly how you get these numbers. Okay, there are some subtleties, but I simplified it a bit for you. But you have really simple model. You have one parameter to describe the coherence, and there are the Wiener terms that describe the atom noise. So these are these guys. Plus now, if you do the measurement, you have the Wiener term that comes from this guy, that is the photon noise. Okay? Okay, but now there's the cool thing about these atomic sensors. You should think of them as a 2-stage sensor. So you have some waveform, which is the outside field. And now, notice that we're not going to sense magnetic field. We're going to encode the field in the pump light. So this was the light used to pump the atoms. It has some envelope, some amplitude. And we're going to modulate it, and we're going to encode there the waveform. Why we are doing it? Because we want the model to be linear and Gaussian. So this is the key. That's why, so remember that this is we're going to encode the waveform in the quadratures of the pump. And why it's a 2-stage atomic sensors? Because you should think of it. You have something encoded in light that drives the atoms. And then in the second stage, you shine light and you read the atom. Okay? So what we're going to do, we actually do the similar thing, but we do it by electronics. And we're really going to drive this to be also an Ornstein-Uhlenbeck process. So these are the 2 stages. We're going to drive a waveform, which will be an Ornstein-Uhlenbeck process, which we perfectly know, and we do it. Plus, it's going to be encoded now with this coupling here on atoms, which are also obeying an independent Ornstein-Uhlenbeck process. And on top of that, it's going to be measured, which has, okay, maybe a Wiener process, because there's no decay. But the subtlety in experiments, normally they only can sample at finite time. So when you come from stochastic background, there's also the subtlety that you shouldn't be really using stochastic calculus here. You really need to take into account that you're sampling in finite time. Okay, but as I told you, I'm not lying. The model is linear Gaussian. Okay, you can even be more smart. You can say actually the model is not just atoms and light separately. You can create like this state of your system, which is the direct sum of the vector describing atoms and the input. And actually, this is now the model that kind of evolution is evolving atoms and input at the same time. And the observation is very simple because the observation model is just a number. It's just this number of the photocurrent you measure. And as I say, I'm not going to talk about this. Actually, in real, I think we need to use what's called a hybrid Kalman filter because the evolution is continuous, but the measurement is actually finite sampled. But this is all well in the literatures. This is 70s. Engineers know this. Okay, so it works. So this was the spoiler. So this was the signal we apply. It's the Ornstein-Uhlenbeck process in the pump. This is the output of the atom, which is smeared. And now we do the Kalman filter. This is our estimate, and I'm estimating only the input of the pump, because I would like to verify that it works. So actually the pump I control, so I can have an access to it. But the cool thing, which I really like, maybe it's not well seen, is that actually you take some kind of a fraction and you do the Fourier transform of it. So notice that input had many features which were completely washed out if you naively read the atoms. But thanks to the filter, you recovered these features. So now if we, for instance, zoom in on this kind of slice of 5 milliseconds, so what is the really important one is this middle bit, because here I'm plotting the real pump, what it was doing. I mean, its average value. I took out the stochastic noise, so it's easy to see for you. But now here I switch on the Kalman filter, so you can see what Kalman filter does. It starts to follow the pump, and there's some kind of time at which it's exactly reflected here. It has to stabilize, and then it keeps on following the pump. And obviously there's stochastic noise on top. And actually this is the thing I mentioned, that first of all we focus on pump because we control it, so we can directly compare it what was the real signal, but also the stabilization of the filter is also a verification that the model was correct. Okay, I have 5 minutes. Okay, very good. So in the last 5 minutes I want to say that we went slightly further. So we said, okay, we have this model, there's no back action, but everything is working. Could we somehow do something smarter? So you should already say, okay, you were applying a stochastic signal that you already knew from the first place. So couldn't we go in this direction of tracking, of applying size signals that you don't know? Sure, Kalman filter will not be optimal, but we know in real-life applications that Kalman filters actually work even if you don't know the inputs. So let's do something simple. So what we did, we said, let's apply some waveforms that we not going to tell the filter. So we chose something simple, which is triangular waveforms. Okay, you'll see why, because they are triangles, so they have just derivatives and kinks. But then you have these things which are kinematic models. So it's a very simple idea. Imagine that now you want to model your finger on the touchpad, but you don't want to say that you exactly know the dynamics, but you know roughly that the acceleration is constant. Right? So I'll follow any dynamics, but the acceleration is constant. So what I'm going to do, it's a standard trick, and these kinematics models are, I'm going to actually treat position, velocity, and acceleration as independent variables. Okay, now I need to relate them because, I mean, velocity is the differential of position and acceleration of velocity. But now I'm going to put noise on the acceleration. So you should think of that. I'm assuming a model that gives loads of freedom. So somehow, these kinematic models give freedom to what the dynamics are. We're going to just say that on average, the acceleration is 0, but it's stochastically fluctuates. Okay, and let me finish with these results. And actually worked. So what we did, we applied these waveforms. The waveforms were triangular. Okay, and you can guess why we did triangular waveforms, because triangular waveforms, only you care about is that it's a fixed velocity, because it's a fixed gradient. The only problematic point is the kink. No? The kink is where the filter is, things are nonlinear, and you can see it. If you apply naively the filter like we did before, this is the green line, it always lags behind the thing. But now if you do this trick, this is the red line, there's two things you need to actually pay. Because you introduced more variables, it's going to be more noisy, so the red line is slightly more wiggly, but somehow it doesn't have this constant drag. So actually when you compute this, it's nice, because what happens is you see the variance of your filter is worse, but the bias is much better, so when you do the mean squared error, you gained. So even though you gave it some freedom, you had some kind of more natural noise, you're actually able to estimate better. And moreover, you can actually directly estimate the slope of the curve, because this filter gives you this. This is part of the, so the red line is estimating the slope. This is the real slope. I mean, it's a square function. And if you naively just differentiated the green one, you'd get something that you'll never be able to resolve. So on the last slide, let me just thank you and mention that this is really the group of Morgan. These are the guys that did the experiment. Ricardo Jimenez was really the person implementing the Kalman filter. And Morgan obviously was the boss. It was Gian Vito, who was doing this noise spectroscopy, Cara and Alexandra doing the coils, and this is me, and I hoped you enjoyed my talk. Thank you.